Okay, this one is on 4.1, number 18 of related rate problems. So, number 18 says a boat is pulled into a dock by a rope attached to the bow of the boat. Passengers are pulling the dock that is 1 meter higher than the bow of the boat. If the rope is pulled in at a rate of 1 meter a second, how fast is the boat approaching the dock when it is 8 meters from the dock? Okay, that's a mouthful. See, first thing is you draw a good picture, which is the hardest part. So here's my boat. That's a pretty good boat. Here's the rope. It's attached to the bow and it goes up like this. And it's 1 meter higher than the bow of the boat. So here's my triangle and this is 1 meter. And when we want to know, let's call the distance, okay, this distance of let's call the hypotenuse D. You just got to give things letters, so call it H, call it D, I don't know, that distance, that's the distance that the rope is being pulled in. The rope is being pulled in like this, right there. But the boat isn't going up, the boat is going this way. So let's call that X, because that's in the X direction, how fast the distance the boat is moving, right? The boat's going this way. And we want to know how fast the boat is moving when the boat is 8 meters from the dock. And did I say feet earlier? 1 meter higher. Yeah, 1 meter, so everything is in meters. And the rope is being pulled in at 1 meter a second. Okay, so when it's 8 meters from the dock, so this distance here, we want to know in this distance when x is equal to 8. Okay, so x is changing, but we want it when x is equal to 8. This is 1 meter high, and we know that d dot, how fast d is changing, we know is just being pulled in at 1 meter a second. So d dot is 1 meter per second. And what we want to know is x dot. We want to know how fast the boat is moving. And again, d dot is dx dt, is dd dt, which is awkward to write, which is why I like the dot thing. And dx is dx dt. Again, a lot easier to write the dot than write that thing out. Okay, so now we have to relate everything. And looking at this, we have a triangle. We don't need angles, so we know there's no sine or cosine. That's one thing you can do with triangles. We could do similar triangles, except there's only one, so there's nothing to be similar with. So probably what we're going to be using here is the Pythagorean theorem. So if we use Pythagorean theorem, we can say that x squared plus 1 squared is equal to d squared. Okay, that's pretty easy. Now we take the derivative with respect to time of everything, that whole equation. Derivative of time of the whole equation. Derivative of x squared is 2x times the derivative of what's inside, so it's x dot. Derivative of 1 is 0. That's nice. And so that's equal to derivative d squared, which is again 2d times d dot. 2's cancel. We want to know what x dot is, so x dot is just d times d dot divided by x. Okay, we're almost done. X is 8, so we know that x is 8. D dot is how fast the rope is getting pulled in, that's 1. But we don't know what d is, so we're going to have to use the Pythagorean theorem and solve for d. We need to know how long the rope is when x is 8 meters to figure out how fast the boat's moving. So let's see, we'll do that over here. So we know that d squared is equal to x squared, which is 8. So I'll just change that into 8. Ha, that was pretty good. D squared is 8 squared plus 1 squared, or d is equal to the square root of 64 plus 1 of 65. So d is square root of 65. So our x dot then is d is the square root of 65. D dot is 1, so don't really need to write that. X is 8. So it's just the square root of 65 divided by 8. Now I know the square root of 64 is 8. So the square root of 65 is going to be just a little bit bigger than 8. So something a little bit bigger than 8 divided by 8 is going to be just a tiny bit bigger than 1. You could leave it as square root of 65 over 8. If we did the math, which sure I'll do it, 65 square root divided by 8, I get 1.0078. So 1.0078, and this would be in, looks like meters per second. And it makes sense, it's just not much faster. If the rope's being pulled in at 1, the boat's only going a little bit faster because it's only 1 meter above the ground here. So it doesn't make a big difference. If that was much, much, much bigger, it'd probably be a much bigger difference. But in this case, they're practically the same. So just a little tiny bit faster than what the rope's being pulled in. Now, if the closer we get, the only thing that's going to change, well, actually both things change. D changes and X changes, but I think the closer you get, the faster it's going to go, but you'd have to figure that out. So I think that's the way it would work. All right, that's number 18. Again, hope that makes sense. The whole trick to doing these is drawing a really good picture, putting in letters for the things that change. So even though, like I said here, X changes, even though it's 8 when we want to know it, it's still always changing. We just want to know what is X dot when X equals 8. And so you draw your picture, use a relation like the Pythagorean theorem to relate the things, take the derivative with respect to time, you get a lot of dots. It's always implicit differentiation where you get dots and stuff and solve for what you want. Sometimes you got to go back like here and figure out one of the things, like we had to figure out D after the fact. And that's just the way that works. And many, many times you got to go back and figure out something else to figure out your final answer. All right, thanks for listening.